Happy Thursday. We're done with techniques of integration. Now looking at applications. First one might be a review for some of you. Looking at area between two curves. The idea is fairly straightforward. And we're given two curves, f of x and g of x. And let's say we want that area. We know the area that's strictly under f, right? We know the area that's strictly under G. Well, isn't the area in question the area under F minus the area under G? Right? But we know integrals are linear. So there's the area. It's fairly straightforward. I'm going to plot the region between the curves of sine of x and cosine of x from 0 to pi over 4. And we'll go ahead and find its area. Right? And I'm not going to do defined yet. So if we just plot two functions, right? The command is plot. Right, so this is used to plot functions of the form y equals f of x. Right, so all we have to do is type in the function. Since we're plotting multiple functions, we just enclose them within braces. First one was sine of x. Second was cosine of x. Now we just need a domain. We can go with a general minus 2 pi to 2 pi.
Why not just the domain we care about?
You'll see why. And that's technically all we need. All right, so if I go ahead and execute that, shift enter, there's what we get. Yeah. Not a fan. I'm going to adjust some options. First option I'm going to adjust is I like to actually label my axes. I'm also going to have both curves be black. All right, so now with those options, this is what the plot becomes. There's a problem with that now is at quick glance, if you know your trig function, you know which one's sine, which one's cosine. And what if I'm lazy and I don't want to try and figure it out? I just want to be able to look and tell. So I just use plot labels expressions. That one's take forever to run. There we go. All right, now it tells me which one is sine, which one's cosine. There's a reason why I called that plot 1. So I'm now going to do plot 2. Again, for this part, I'm going to do the equals just so you can see what it's doing. I'm again going to plot the 2. This time over the desired x interval, 0 to pi over 4. I'm not going to label this one. And I'm going to fill it. Yeah. So filling is going to be between the first graph to the second graph. I just have to pick a color. I haven't looked. Okay, hell you, go away. Perfect. Lila. Why not? I'm here for the RGB code. Copy that. RGB color. I'm going to now those in. Now, mathematically, once these as decimals, let's divide each one by 256. Because the RGB for each red, green, and blue was a number between 0 and 256. Now, if I execute this one, that's what we get.
So what was the point of doing all the fancy drawing? Just because it makes it look nice, or
What do you mean?
like you could also just look at the first graph you made and see it.
Right, but then doesn't fill it in for me. Now watch. I'm now going to use the show command. To show plot 1 and plot 2, and now we have our shaded region. There is a method to my madness most of the time.
What's rest of the second box? Yeah, then you have the RGB style of that color.
You don't have to. You can. It has some defined colors like blue, black, orange, yellow, red, green, magenta. But if you really want to get fancy, you can just look up an RGB code and use that. So there's the region whose area we're trying to find. First thing that you should ask yourself, over that region, do the curves intersect at all? Technically just at pi/4, right? Which is the endpoint, so it doesn't really, we don't care. Perfect. So we don't have to worry about splitting our interval up. Our interval of integration will be 0 to pi/4. Now we just have to decide which function is larger. From a graph, it's very easy to see. Cosine's larger. Right? If you wanted to do it algebraically, just pick any point in the interval. Plug in that point to both sine and cosine, and whichever one gives you the larger value is your larger function. We're 0 to pi/4. Cosine x minus sine x. I would just go ahead and evaluate that integral. This is not a terribly difficult integral to evaluate. So I'm just going to do it by hand. But remember, at this point, you can just use a calculator once you set it up.
You're gonna be using whatever the site is for the quiz today? No.
Quizzes, I'm not ever going to make you use Mathematica. The tests, maybe. Antiderivative sine x plus cosine x, right? Evaluate that from 0 to pi/4. Sine of pi/4, 2/2. Sine of 0, 0. Cosine of pi/4 is √2/2. Cosine of 0 is 1. Our area is √2 minus 1. And leave it exact. Unless the problem specifies for a decimal approximation. So region between 6x minus x squared and x squared minus 2x. Then we'll go ahead and find its area. All right. I'm also going to set the plot range. So I'm going to set the y-axis to go minus 10 to 10. Otherwise, it does it automatically.
How do you get the arrows?
It's just hyphen and then the greater than sign. And it'll automatically turn it into an arrow. Right. So here's where we're going to now run into a bit of a problem. So let me store that. And then let me call plot 1. They didn't give us points of intersection here. Right? They didn't give us an interval. So we have to determine the points of intersection. Looks like it. But you can't say for certain it is. Two ways to do this. You can do this by hand algebraically, right? Set the two functions equal to each other, solve for x. Or we can just let Mathematica do it for us. Notice I'm doing double equals. Solve it for x. 0 and 4 are the points of intersection. Copy and paste. And then just adjust things. All right, so I'm going to go 0 to 4. Keep that, keep the plot style, but now I'm getting rid of plot labels. And again, filling graph 1 to graph 2. Now for the style. It sounds cool. Actually don't need to divide 0 by 256. Just leave it as 0. So there. Region I can get really fancy. And actually also label those points of intersection. I really wanted to. I'd have to use the graphics command for that. Graphics command and the point command. I can also the tix command. ticks on the x-axis. I'm just going to do the 2 points of intersection, 0 and 4. And I'm going to leave the y-axis blank because I don't care. Right, so if I re-execute plot 1, that's what that looks like. Now I have to do is re-execute my show. And that should be sufficient. So set up the integral. What will our integral be?
Minus x squared. All minus 6 squared minus 2x. And therefore,
What was it?
x minus x squared
All minus.
minus x squared.
What about the interval? And so there's the setup. Simplify it. Again, this is a fairly straightforward integral to take, right? Antiderivative negative 2/3 x cubed plus 4x squared. Start that from 0 to 4. What is 4 cubed? Yeah, negative 128 over 3 minus 0 plus 4 times 4 squared minus 0. (64 times 3, 192 minus 128.
64.
64. Our area is 64 thirds. That's That should. I see what I did there. Region between y squared equals 4x and y equals 2x minus 4. There are two ways to tackle this. We could try and write the y squared equals 4x as two functions of x. You have one being 2 root x, the other being negative 2 root x. And then do it that way. Or we could write the y equals 2x minus 4 as a function of y. And then integrate with respect to y.
But I mean, we know y equals 2x plus 4 is always going to be above 0. Wait, no, never mind. But the other my short. I thought you could ignore one of the other functions.
And nope. Let's try that. Well, the first thing is let's just go ahead and get a plot. And I'll figure out what to do from there. All right, so I can't use plot. Right, because plot is for y equals f of x. If I want to plot relations, I'm gonna have to use the contour plot command. I'm gonna say y squared equals 4x. Again, notice it's a double equals. And then y equals 2x minus 4. And so we need domain for both x and y. I'm going to go the standard viewing window minus 10 to 10 all the way around. This would be technically all we need. There is a problem. That's the default option for contour plot. Not really useful.
Why not?
Well, where are the axes?
Well, you can see them. They're at 0. Then the center.
Right, but they're not actual,
And you can kind of like put them on there.
right?
You can see it enough.
But I'm lazy. I don't have to think too hard.
Okay.
Oh, that's right. No, it's not box. It's frame. So I'm going to turn the frame off. I'm going to set the axes on. Ah, that's better. I like that. Now I don't have to think. This time contour style, once again, that's going to set the curves. I want them both to be the same color. Because the default colors for Mathematica are hideous. So there's our region. It's gonna be this bit in here, isn't it?
How do you do this if you didn't have any calculator or graphing? Well, I mean, I guess calculator for like basic stuff, but no graphing.
You'd have to do everything algebraically.
I mean, I imagine you can kind of visualize it. Well, let's say you couldn't.
You wouldn't be visualizing it. You decide whether you want to do this as a function of x or y, then set the functions equal to each other to get the points of intersection. Then you'd have to, of course, plug in points to determine which function is larger.
Would it be 0 to 2?
It depends on how you want to do this. Right? Are we going to integrate this with respect to x or with respect to y? Because that's going to determine our setup. You can do both. Just a matter of which one's easier. Y is easier. So I want to try something.
Y squared function, couldn't you just square root both sides and just make it y equals square root of 4x?
Right, but it's not just y equals square root of 4x. There's two of them. You'd have positive and negative.
I feel like integrating with respect to x shouldn't be too hard because you only have two things you actually need to integrate, and the other two are triangles.
You don't have two things you need to integrate.
Well-
Well, you're gonna have two areas you have to integrate,
Yeah.
yes.
Two areas
Right.
you have to integrate, and then there's two triangles you can draw to fix the rest.
You won't need any triangles to fix it if you set it up right.
Well, okay, if you set it up. Oh, that's true, yeah. I was thinking of setting it up without combining them.
Well, if you set it up right, you just need two integrals. That's all you would need. Because that's how I did it the last time I taught Calc 2, is I set it up with respect to x, not with respect to y, and it's just two integrals. It's two regions you have to integrate. I'm going to see if I remember the region plot command. Let me look it up. I think I can use this, and I think it's going to be nice. Yep, I have to pick an x. What? Yep, perfect. Okay. I'm going to define this as functions of y. So x is going to fall between what and what? Well, clearly this is the lower bound, right? And then this will be the upper bound. So I'm going to go y squared divided by 4 less than or equal to x less than or equal to, and I'm just doing less than and then the equal sign, and it automatically converts it. Y minus 4 over 2. And again, I have to pick x and y, so let's just do that. This should work. It didn't. What did I do wrong? Oh, that shape doesn't look.
Oh, is it because it should be y plus 4?
Oh, what is it?
Well, it's minus 4 originally. So that
Derp. Perfect.
square function is less than the. I would say that would be. That'd be fine. It looks like it'd be fine.
Right, but you're not doing X, you're doing with respect to Y. So it's not up, down, it's left to right. Right, so again, I'm gonna adjust some settings. Frame, false, axes, true. Boundary style. Also gonna do black, and then it's the region style. Uh-oh, no. No, that's not gonna work. That's definitely region. Where are my options? Details and options. Right. Oh, must be plot style. Before I do anything fancy, I just want to see. Yep, that's it. Perfect. What color? Latte. Go for a latte right now. Oops. Choice C. Okay. Now what I'm going to do is I'm going to call this plot 1. This plot 2. And since we've decided now that we're going to do it as functions of y, y squared over 4 is equal to, use the right operation this time, y plus 4 over 2, solve it for y, -2, +4. So I'm going to leave my x's blank, and I'm only going to use -2 and 4 on the y-axis. And there we go. There's our region. I set the two functions equal and solved it. Oh, hold on, wait. Okay, the problem here is it's not going to let me, with contour, I can't actually put labels in. I can only do a legend. But the legend requires the curves to be different colors, which aggravates me. So we're just gonna have to make do. I mean, I could manually put it in. But I'm too lazy for that. Write it next to here. So set up the integral. What is it? And so what's the integral? What's the setup?
The y over 2 plus 2 minus y squared over 4.
So y over 2 plus 2. And he said what? He divided everything by 2. So you just split into 2 separate fractions.
Yeah.
Oh, should be dy, right? Yeah. What about the limits of integration, the bounds?
The y squared over 40. Because that would be the top of the.
But because it's with respect to y, it's not top to bottom.
Flip it. Side, but at the top. Side on top.
You rotated it the wrong direction. Right, you rotated it clockwise. It needs to be rotated counterclockwise. But don't worry about that. When you're doing with respect to y, it's red left to right. So right is larger. Right, so this is the upper bound. And this would be the lower bound, right? And again, this should be a fairly simple integral to evaluate. Four squared is 16 divided by 4 is 4. Minus negative 2 squared is 4. Over 4 is 1, right? Then we're going to get plus 2 times 4 is 8. Minus 2 times negative 2 is negative 4. Minus 4 cubed, 64 over 12. Will be what, 16 over 3. Then it'll be minus negative, which will be positive, but then negative 2 cubed is negative, so it stays minus. 8 over 12. Two over 3.
Wouldn't it become positive?
There's 3 negatives.
Well, yeah, there's 3 negatives
Right.
times another negative.
There's 2 negatives times another negative, right? Minus,
Minus.
the minus makes it positive.
Oh, yeah, that. Never
And
mind.
then negative 2 cubed makes it
I forgot the.
negative. Yes.
Oh, you do, okay.
I just do it for each one individually. Right. So I evaluated y squared over 4 from 4 to negative 2. Right. So it was 4 squared over 2 over 4 minus negative 2 squared over 4. I did that first.
Oh,
I find that easier to do in my head than trying to evaluate the whole thing at 4 first and then 4 and 4 is 8 plus 8 is 16 minus 1 is 17 minus 18 over 3 But 17 times 3.
D1.
Something's wrong.
But I'm pretty sure you're supposed to do 15.
Wait,
minus-
yeah. Okay, I can't do basic arithmetic. 45 minus 18, yeah, that's going to give me what I want. 27 over 3, which is 9. Our area is 9. And again, you could also just plug this into a calculator to do it. So, couple comments before we move on. We're in applications of integrals now. Your setup for the problem is 70% of the points. So if you set up the integral correctly, it's a 7 out of 10 right off the bat. Then the evaluation will be the other 3. You can just plug it into a calculator to evaluate it. If you do that, be careful. Because if all you do is plug it in and then write down what it gives you, if that's wrong, you lose the full 3 points for the wrong evaluation. Whereas if you show the work for the evaluation, I can give you partial credit on those 3 points. So it's up to you. So the region between x cubed minus 6x squared plus 8x and the x-axis. And then we'll find its area. Remember, what does a normal integral give you? Gives you a signed area between the curve and the x-axis. Which means if you have anything below the x-axis, it's actually going to cancel out area. You can set up as a basic integral, but you have to do something to the function, which we'll discuss. So your hand?
No, I was gonna say that basically. Although, what would you do to the function that doesn't make it hard to integrate?
Wow. It's technically not hard. You just have to split it. You have to take the absolute value of the function.
Yes.
So the regions that are over it, right? So you have to split the integral up based on the regions above and regions below.
Well, yeah.
For the regions below, you multiply by -1.
Then you still had to split it up.
Right. But that's mathematically how you do it. But we have to find the plot anyway, so.
Why do you have to find a plot?
Because it told us to plot it.
Oh, okay.
I'll just use the standard viewing window. And so there is the first plot. Means we're going to have to solve. So what is the function going to equal? I think if I just do that, that will give me what I want. Oops. Yes, it does. Except, forgot to do this. Go.
You scroll up just a little bit.
Since we're interested in region between a curve and the axis, we're just using filling axis. So I'll fill the entire region between the function and the axis. Told us we had to get the plot.
Is drawing it good enough?
Got a rebel over here.
Is drawing it good enough?
Nope. Have to use technology. Set up the integral.
The integral of x cubed minus 6x squared plus 8x dx from 0 to 2, and then the same thing but from 2 to 4 times -1.
Yep, there's your setup. This is again a fairly simple integral to do. Two to the fourth, 16 over 4 is 4. Minus 0 is same thing, right? So minus 2 times 2 cubed plus 4 times 2 squared. Oh dear. 4 to the fourth over 4. Okay, that's just 4 cubed, so 64. Minus 2 to the fourth over 4. It'll be minus 2 times 4 cubed minus negative 2 times 2 cubed. Oh, go away. Plus 4 times 4 squared minus 4 times 2 squared. Before 64, 128 minus 128 is 0. Good, that's gone. 16 minus 16 is 0. That's gone. So it becomes minus negative 4. Area is 8. If you were just to set up the integral from 0 to 4 of the function, you get 0.
So is there any way, or rather, more like, does this hold more generally that on cubic functions, they're gonna have symmetric areas like that?
You can. Right?
But
'Cause
like,
cubic by itself is symmetric about the origin.
so assuming you don't have any like plus constant in your cubic, would it always do that?
No. This one just happened to give you symmetric areas. Right? It's not always going to happen, but it can.
Yes.
The area is negative, yes.
That's bullshit. They cancel out.
Right. But we're not looking for signed area. We're looking for area of the region. So you want it to be positive. Right, so that's why we did minus the second integral to make that area positive. Right, we don't want them to cancel, we want them to add together.
Would the areas be like, now obviously it doesn't always have to be the x-axis, but let the, if you drew the like x equals the y value of like the vertex, if you call it that, of the cubic function.
Well, cubic doesn't have a vertex.
Well, I mean, basically the center point.
Oh, that is symmetric. Well, again, cubic is symmetric about the origin.
By default, but like,
Right.
I'm talking in general.
So then what you'd have to do, yes, you'd have to make x equal whatever it is, right? However it shifts. Then it'd be symmetric about that. Not about the line. Right, but it'd be, if you want to just shift that and call that the new origin, it'd be symmetric about that new origin. Or you have to shift you have to shift the axes. However the function shifts, and then it'd be symmetric about the origin again, yes. Right?
So theoretically, if we knew that beforehand, before the problem, and we noticed that this function is at x equals 0, we could have just done 2 times the first integral.
If you recognize it's perfectly symmetric. Yes. How would you recognize it's perfectly symmetric?
Well, you know that since it has,
And remember, this is not just a basic cubic. Because has an x squared and an x term attached as well. Which changes how the cubic behaves. Right, because this cubic is not symmetric about the origin. Right, just so happens that our desired region will end up being symmetric.
but it is symmetric around 2, 0. It's symmetric around 2, 0 though, right?
The entire function, no.
No.
Right, if it was, this hump would be up here, wouldn't it?
No, I meant symmetric in the way it's symmetric around the origin. So like it would be odd around that point.
No. This function is neither even nor odd, so it has none of the basic symmetries. Right, this little region, right? If you just look from 0 to 4, that definitely is symmetric. If you just look 0 to 4. Well, again, technically it's not technically symmetric. Right, the regions happen to be symmetric, right? So the graph itself isn't. Right, because to be symmetric, this would have to move over here, wouldn't it? So this little bit would have to be here. Then you'd have symmetry. Right? Which you don't. What we do is we say the regions have symmetry. Right, because their areas happen to be equal. Right, in order to be symmetric, what is it about the y-axis? It has to be an even function. To be symmetric about the origin, it has to be an odd function. This one's neither even nor odd, so it doesn't have either of those symmetries.
What does it mean to be an even or odd function?
F of negative x equals f of x, that's even. F of negative x equals negative f of x, that's odd. Right, so cosine's even, sine's odd. There you go. There we go. We're going to plot the curve y squared equals x squared minus x to the 4th. And then find the area that is enclosed by this curve. Then we have to do a contour plot. Y squared equals x squared minus x to the fourth. I happen to know I only want to go. And even that's kind of too far. Is this a lemon? This. Get what the shape's actually called. Shape is infinity. A lemniscate. And that's the shape that we're dealing with. Right, so that's what this is. Hmm? Right, we want to find the area that's enclosed by this. I'm fairly certain I can get it to shade it for me if I do region plot again. Would be negative square root x squared minus x to the fourth. Is then equal to y less than or equal to the positive square root. Crap. Oh, just gave me errors. That's fine. It still shaded it for me. That's all I care about. You could.
You also just take only a quarter of it
Why?
because it's easier. You don't have to worry about.
Right, but why can you just calculate area of a quarter and then multiply by 4.
It's symmetrical around both axes.
Not just both axes. This also happens to be symmetrical about the origin. This has all 3 types of symmetry. Symmetrical about the origin, symmetrical about the x-axis. It's also symmetrical about the y-axis. What that means is this total area and this total area are going to be the same. So if we find this area and double it, we get the total area. But the area above the x-axis and the area below the x-axis are also the same. So if we take the area above the x-axis and double that, we'll get half the area. So just calculate this area over here, multiply by 4, and you get the total area. That makes setting up this integral a lot easier. Before times integral from 0 to 1. Square root of x squared minus x to the 4th dx. Right, this is finding the area that lies above the x-axis on the right-hand side. Right, so it's finding that area and then multiplying it by 4. Oh, that looks like a hideous integral. It's actually not. This is actually a very nice integral. You can factor out x squared. Now it becomes a simple u sub. However, I'm going to take this opportunity to show you how to do integrals in Mathematica. Integrate your function. So the integrand, I'm going to do this one, x squared minus x to the 4th. Because we're doing a definite integral, right? We're actually doing an integral, not an antiderivative. We're putting braces. The variable we're integrating with respect to, lower limit of integration, upper limit of integration. Shift enter, we get 1/3. Right, we just have to multiply that by 4 and we have our total area. Any questions on area between curves?
You like the code?
Oh, so you made it square, like you made the integral square root of x squared in this episode was because of the last one.
Because I want it in the form of y equals f of x, yes. Which code do you want?
Why did the y have to equal plus or minus in this scenarios?
Because I'm only integrating 1/4 of it. Right, so which region am I integrating? That curve is positive, isn't it?
Yeah.
So that's why y is positive. This one would have been negative down here.
Problem above, it had to equal you. With the last one, with y squared equals 4x, the other problem.
Right, that had to be plus or minus, yes.
As it had negatives.
So if you actually look, right, when I plotted this region, I did do negative, positive, right? Yes, but when we integrated it, I was only integrating a quarter of it. That's why I ignored the negative part. Anything else? So I actually forgot to print out quiz. So just pull out a sheet of paper. Make sure you write your name and quiz 8. Do it on the loose leaf paper and then turn that in. All right. So notice it says to set up the integral first, so I definitely want the integral set up. And then you can use a calculator to actually evaluate it. Huh?
Uh,
Well, I mean, a teeny bit would be like a micrometer, right? So I just did.
no.
I'd say a big teeny bit would be a millimeter.
That a negative x? There y equals e to the negative.
Thank you.
Actually, a micrometer is not even a teeny bit. A nanometer would have been. Don't forget you have a test due by the start of next class.